Okay, so everyone have a good lunch? Yeah. Good, so let's start the talk. So the next speaker will be Jeremy Kerr.
Thank you.
Yep. He'll be talking LibreBMC. Literally everything is open. So Jeremy Kerr is a Linux and open source system developer working on the kernel, drivers, firmware, and related plumbing. Today, Jeremy will be describing the completely open baseboard management control system, LibreBMC. So let's welcome Jeremy.
Thank you very much. Thanks for the warm welcome. Firstly, I would like to acknowledge the traditional owners of now, the Wurundjeri Woi Wurrung people of the Kulin Nation. As maybe indicated by my pronunciation, I am a visitor on this country. I'm from the Whadjuk Noongar country over in Perth, and a lot of this work was done on that country there. I would like to show my respect for elders past and present. By way of my intro, my name is Jeremy. I run a little open source embedded systems programming consultancy called Code Construct. I'm very proud to sponsor Everything Open this year. And before we get into the kind of technical bits, a couple of credits and/or disclaimers. Firstly, what I'm presenting today is built on a lot of existing code that's written by people that are much smarter than I am. Some of those folks are in the room today, so I'm going to warn you there's going to be some oversimplifications as well in the talk. What we've done essentially is kind of taken a lot of that work from these clever people and kind of glued it together, done a bit of bring up and done a few fixes and built something that we can actually talk about at a conference. This work is definitely a big collaboration between Code Construct, the Open Power Foundation, which Hugh mentioned earlier in his keynote, and IBM as well. So thanks to those folks for participating. So what are we doing here? Our general plan is a two-step thing. We're going to get a server, we're going to take out its BMC, and we're going to put a more open sourcey BMC into it. That's my talk, thanks all. No, what's a BMC? So a BMC is a acronym for a baseboard management controller. And essentially the management controller that's responsible for managing and booting and to a lesser extent sort of controlling a server in a data center. So things like being able to remotely turn on and off a computer, being able to inspect its inventory while the main part of the computer itself is off, being able to get a console on it, all the sort of the remote things that are sort of sidebands to the main computer itself, the BMC is responsible for. Why are we looking at open source BMC? Essentially, there's a lot of side channels involved here. And having a somewhat mysterious computer that's talking to your actual computer can be a bit of a risk. So back at LCA in 2021, I presented a bit about kind of what we're doing in the BMC space, and it included these two slides. On the left, a bit of a system diagram about what the host might be able to do, accessing sort of parts of the BMC over one of the buses between those two devices. There was a CVE recorded, 6260. It's not a huge issue, and for most applications where we're using a server with a BMC, it's kind of not a problem, but it can be depending on your trust model of how you're using your server, who has access to the BMC, who has access to the host, and if those need to be separate. So while it's not a serious problem, it's a kind of demonstration of some potential issues in that pretty much every server kind of 2019 and earlier had this potential issue. And it's exposed by essentially the fixed piece of silicon that is the BMC and how it operates, how it interacts with everything else in the system. But instead, what we're going to do here is apply kind of the concept of an open ecosystem and open sourcing everything into making that BMC part a bit more verifiable, a bit more trustable, a bit more modifiable, because we're either writing the source ourselves or we're using bits that we can inspect and trust and modify. So in doing that, we're going to start going to go up the stack, starting from hardware. And of course, we're going to start with open hardware. We're going for an open approach to everything here, starting with hardware. And I guess for extra credit here, we're going for not just the BMC, but also some elements of the host server as well. What we're going to be doing is we're not going to re-implement the entire thing. We're doing a BMC bring up against existing host server hardware. And we want to choose a platform that we can actually inspect a bit and do our bring up without having to do too much reverse engineering. So we've got to choose a platform as a target. And as was mentioned in Hugh's keynote this morning, open power platforms are a pretty good choice for that. The repo here contains essentially all of the firmware that's running on an open tower server. So we can look at it, we can inspect it, we can write the bits that talk to it without having to sort of make too many assumptions about things. And that's going to be exceptionally helpful for our bring up for sort of reasons I'm going to talk about later. Being open source, we're not going to modify it, we're still going to use it as a reference for our BMC work here. So we've kind of chosen open power as a base for this, but that's more of an ecosystem. What we need is a specific platform. Back in June 2018, this system here, the IBM Oak Ridge Summit supercomputer, was announced as the highest performing supercomputer of the time, according to the top 500 list. And it's composed of about 4,600 of these individual nodes, all networked together. And those individual compute nodes have this catchy name, the AC922. And that's what we're going to choose for our bring up project here. So we're going to get one of these servers, take out the BMC, and put our new open sourcey BMC in it. This is the insides of one of those machines. It's a 2-socket, 128 threads, 2-rack unit device. Here we've got a lot of empty space. There's carriers for a lot of honking GPUs in there. It's definitely a production server. It was part of the fastest computer in the world for a while. It's definitely a high performance server. So we're not kind of just doing a toy bring up project. This is a serious bit of kit.
Did you literally go and pull one out of production effectively?
I borrowed it. It's yeah. We will send it back at some point. Yeah. The Oak Ridge is not missing one of their nodes. It's all right. As well as having, I guess, an important design point about this platform is, as well as having a fairly open architecture and open design, the BMC itself is socketed. So that's going to be pretty handy for us. If we look at a GA x86 motherboard, this is a server board here, kind of similar, 2 sockets, 8 DIMMs per socket. It's about the same sort of generation as our AC922, but it doesn't have those space for the 6 GPUs. It doesn't really matter for this. But if we look at the bottom your left of that, we've got this little space here, and that circled thing is the BMC. Now, I'm pretty handy with a chisel, but I don't think I could get that off without ruining the entire thing. So the astute hardware folks are going to see that this is not something we can just take it off and replace it with a new one. Whereas on our 922, this is the BMC that's shipped with the machine. So as you can see here, it's on a separate board. We can unplug that and put our new thing on it. So that's got a much better chance of success modifying this platform than our earlier one. So this, like I said, existing BMC, that's what we're trying to replace here. So reviewing our progress so far, we have a server. I'm going to kind of build on this. The project managers in the audience are going to love these slides. We kind of build up as we go. So we have a server. We have a server that we can do a bit of experimentation on due to the open nature of the stack and the platform and the implementation. We can remove the BMC, but of course, we're going to want to add a new one to that. We can't just operate this thing without a BMC. So before we kind of go into that, a bit of a digression into a bit of a technology that's happening at the moment called DCSCM or DCSCI. A couple of acronyms that are going to help us with our project here. The clever folks at the Open Compute project have published a standards. Kind of heavily, the authors here are essentially Microsoft and Google. under I guess, an effort to make their own systems production more modular. So by producing a spec about what a BMC should look like and how it connects into the system, there's an effort to possibly use new parts, make a system out of more modular components. And kind of having a standard rather than having to do everything from scratch for every platform. So that gives us a bit of a standard form factor for a BMC and a standard connector. The architecture of that standard, so there's two parts there. The DCSCM is the module itself, so the BMC module, which has a size and a connector and everything. The DCSCI is the connector definition. So the intention here is that you have your BMC, you have all of your signaling go through this DCSCI connector, going to all of the bits that it's managing. So your peripherals, your board, your host CPU, and it's doing all of its temperature management, CPU boot, all that kind of thing over this one connector. This is what the connector looks like. Again, if you're sort of following the hardware side of things, you might recognize this from connectors such as the SFFTA1002, which is a... Oh, my button came back. Or it'll all happening at once. Anyway, it is the protocol-agnostic, multi-lane, high-speed connector. And when they say multi-lane, they are not messing around. So this is what's carried over that connector, and this is essentially the stuff you need to implement a BMC. So all sorts of different signaling, some of which is used on some platforms, some won't be used in some platforms. And that basically gives us a standard form factor to connect these kind of things into the base platform and do all our servery bits. So specs are all great. This is DCM, DCSCI, but we need an actual implementation. And on our open source tilt here, we want an open implementation. And this is one of them. So this is a board produced by a manufacturer called Ant Micro. They have designed and produced this board called a DCSCM board. It is this DCSCI connector down the bottom there, basically with all those lines going into an FPGA. It has some onboard RAM, so we've got 512 megabytes of RAM. We have a network connector at the top. We have a little bit of storage and some eMMC device there. And we have all the little bits required to manage an FPGA. So we have a programming interface. We have some USB in which we can interact with that FPGA. And of course, everything's open here. So these are the schematics of that board. If you can find the bug there, I'm very impressed. And where were you 5 months ago? So again, big thing is the hardware is open. The hardware's out there. We can see it. We can investigate it. We can potentially modify it and do our own thing if we want. We're sort of not quite in that business at the moment, but that's, again, the advantages of having things open for us are pretty huge in this case. The source, as I said, is online. This is the repo for that device. You can open pull requests. You can do all sorts of things. Just, I guess, like coming from a software world, it's kind of cool to see that we can have those kind of designs out there and usable for this. So back to our list. We have a server, and we have potentially a BMC hardware. I say potentially. We'll get back to that in a bit. Another aspect, I guess, of our AC922 server, going back to that original photo, the top right here is where that BMC usually goes, and we can zoom into that area and we find one of these friendly connectors. Basically a massive pin grid with all the BMC signaling to that. And again, the astute hardware folks in the audience might have noticed that that is not that. So we have a bit of a problem here. Fortunately, someone has already solved it for us. There is one more piece of hardware, again, an open piece of hardware, which is this little guy. So big board, not that big, kind of this big, with one of those DCSCI connectors and that massive pin grid on the bottom. And that routes kind of between what the the AC922 server expects in terms of signaling, and the DCSCI on the other side. Now, it's not entirely one-to-one. There's some signals that exist on one connector that don't exist in the other, but we can get around that. And this allows us to do this. So this is our same AC922 again, interposer in green at the bottom, and that DCSCM board on top. So now we have a server actually connected to our potentially of BMC hardware. Now, I did say I would go back to that potentially aspect. If you're producing a system that uses a DCSCM, or actually, I guess any BMC-based system, you're going to have some specialized hardware here. So this is essentially what we would need to implement a DCSCM module. We've got our BMC with all of these kind of different signaling lines going out to our DCSCI connector, and some onboard hardware that's relevant to the BMC itself. The BMC needs to talk over the network, for example. It needs some storage. So there's some specialized hardware on the device. There's a couple of vendors that actually make one of these system-on-chip designs. There's, I guess, two industry leaders that basically own the entire market of what's on a BMC in any server that you buy now. And they produce essentially a little device, has a little ARM core on it, and all of the kind of the bits of hardware that you need out of a BMC to talk things like I2C, FSI, LPC, all the interfaces to the rest of the system. So those already exist in Silicon. What we're doing is replacing it, so we kind of need to we need to design something that works like this. However, what we have at the moment with that DCSCM board is just an FPGA, right? And all it has is IOs. There's just lines going from the DCSCI connector into unassigned IOs on the FPGA. There's nothing about this that makes it a BMC at this point. And I guess more obviously, on a BMC, we have an actual CPU core on it, right? We have an ARM core on it. We don't have that on our FPGA. We just got a whole bunch of, I think, 75,000 logic units that we can turn into something. We haven't turned it into anything yet. So, existing with an ARM core at the moment, this is our blank slate to mess with. We've got IOs, no core, nothing. So we need the bits that turn that blank slate into some kind of BMC. And for those kind of not familiar with the FPGA world, we'll refer to that as gateware. Or it's not quite software, not quite hardware, but we can write some code that will turn into the FPGA bitstream that turns this thing into a usable device. So that's the gateware itself is the Verilog or the VHDL. Whatever we compile into the bitstream defines the behavior of that device to do BMC-like things. Now, of course, this is an open source conference, so we want some open gateware to do that. There's actually a massively increasing amount of open gateware around. There's lots of resources about bits that we can reuse, reapply into our blank slate, and using a whole bunch of different development models to do that. Some folks have written raw VHDL, raw Verilog. Some have written schemes to generate that Verilog out of high-level languages. I'm going to go into that a bit, maybe offline, but there's certainly ways we take open source bits of code to generate behaviors for our blank slate of an FPGA. So going through that, first up, we do need a CPU, and I can highly recommend this one. So there's basically an open source CPU core called Microwatt. This really deserves its own talk. There's a massive amount of cool stuff in there. It's a fully open power instruction set architecture core. It's just missing a couple of things, and they're the vector, like that 128-bit wide registers and register instructions. We don't need those at all for our BMC. We're not trying to produce a high-performance computer on our BMC. This is kind of the server itself is the high-performance computer here. This is Microwatt, can be synthesized for Lattice and Xilinx FPGAs, can also run in SIM. But what it gives us essentially is a way to drop a very usable core onto our FPGA device and have some sort of compute capacity behind that. And super importantly, the Linux port for this is already done for us. So we could drop a Microwatt core there and have Linux boot on that core with fairly minimal effort. So that's going to be our CPU core for this project. We also we've got a CPU, we need some RAM, so we need a DRAM controller. From that, we're borrowing some code from the LiteX project. So LiteX, library of FPGA components, one of which is the DRAM controller. We can that's already plugged into the Microwatt core for us, so that's super. We also have an Ethernet device on our FPGA. We'll also grab the LiteEth module that can also be plugged into Microwatt. This is quite a simple Ethernet device, which already has Linux support. We're not going for super high performance networking here, but it's enough to communicate with our Microwatt CPU. We need some storage, to load our kernel and root file system and all that bits from. All the kind of BMC software comes from our eMMC device. And in order to talk to an eMMC device, we need an eMMC controller. And for that, we're using more LiteX code, the LiteSD project. It has some Linux support. What we can see here, we've got an SD card type controller. We're talking to an eMMC device. So we needed to do a bit of work, and most of that was Matt in the audience here, making that compatible with an eMMC device and the Linux drivers that talk to it to actually support eMMC. But once we kind of sorted that out, we just have the Linux eMMC storage layer talking to this controller, talking to the eMMC hardware on the board itself. Cool. And of course, one of my favorite things, we have a UART. It's from the OpenCores project. It just comes as VHDL. It's standard 16550 UART, so of course it has Linux support, one of the most common bits of hardware. So that at this point, that gives us our CPU core, we've got RAM, we've got network, we've got storage, we've got a serial console, all that kind of stuff. So at this point, we've got our server, we've connected to our basic SoC. So, but it's not quite hardware. We're kind of gateware and hardware distinction is a bit blurry at this point, but we do have a little chip we can run code on at that point. Now back to our diagram earlier. This is what we're trying to make. At one point, we've kind of covered the left. We still don't have any of these bits on the right here. We'd actually make it a BMC, and they're kind of the interesting things for what we're doing here is producing a BMC that can control a server. So we're still missing the dedicated hardware for like the LPC and the FSI and the I2C. So we want to turn our SoC into something useful. So we grabbed a few other bits, one of them being produced by some folks at IBM under the Open Power Foundation project, which is essentially an LPC controller, which is our main, pretty important bus to be talking between the BMC and the server, mainly because it's used for the firmware transfer. So when the server boots, it needs to request its low-level firmware over LPC from the BMC. So it's pretty critical that we have this working. In our architecture here, the BMC is the LPC device, and the host CPUs are the LPC controller. So trying to do this in software is a bit tricky, hence having actual dedicated bit of hardware on our FPGA to do that is pretty essential for that. So it gives us our firmware load, it gives us a bit of a channel of communication between the BMC and the host in things like IPMI and console, host console as well. So we're using the LPC peripheral for that. We also have, in the Microwatt definition itself, there is a GPIO controller, so that allows us to do all of the kind of off-to-the-side bits of implementing a server. Things like the power button, that's basically just a GPIO that goes from the button itself to the BMC that tells it to start booting the server. So GPIOs for that. The Microwatt code already had those present. We just needed to add some interrupt support for that. It's pretty critical that we have GPIO state changes actually interrupting the CPU rather than polling for that. So the IRQ support, that was all you, Matt? You did the... Yep, I think most of the... Yeah, anyway. So we now have the GPIOs that support things like our LEDs, our fan presence, all of those bits there. So going back to what we have so far, this is the system we've built out of those bits. We're starting now to look a bit more like a BMC. You know, we have our core, we have our RAM, we have our bits. Don't laugh at my 100 megahertz computer. It's pretty good. We'll see how we go. But we are missing a couple of devices that I did mention earlier on, and they're the I2C and the FSI buses. Going to get to that? So I2C is used heavily on BMC systems. A lot of like the temperature sensors, a lot of the fans, all those kind of bits. Even GPU expanders, so like more GPUs behind an I2C bus, implemented using an I2C connection between the BMC. And we also have this FSI bus, which, good question, is, what does it stand for this week? The Through Support Interface or Field Service? Anyway, whatever it's called this week. It's an IBM design. It's required, it's a bus between the BMC and the processors that implements kind of the really, like the early firmware load, early or low-level control of the units inside a CPU. There's gross oversimplification, but it's our magic way of talking to the CPU essentially, and doing some really early boot processes on the CPU. There's also a few monitoring applications that happen over FSI. I think we have access to the on-chip controller, so the thermal management over FSI in some cases. So we haven't implemented these in Gateware, but fortunately, in Linux, we have a couple of drivers that are handy for us here. We can take a couple of GPIOs and use them for I2C just by manually toggling or reading those GPIOs. For FSI, we have a back-end driver for the FSI bus that does the same thing. We can just twiddle the GPIOs and get proper FSI transactions working over essentially a raw GPU device. Yeah, exactly. So these are used in production. We're not just hacking things around here. We are introducing a bit of technical debt, and like all technical debt,
It's awesome.
it's sure. Like all technical debt, we're going to kick that can down the road for a few slides' time. So what do we have? We've got our FPGA. This is looking like our earlier diagram. We've got all these signaling happening in actual bits of hardware that allows us to implement things like a BMC. And we have our sort of peripherals like I/O, MMC, DRAM, all those kind of bits are now implemented on our little device here. So back to our slide. We have a server connected to an actual BMC. Good stuff. So we have hardware, right? We have our hardware sorted out. It's not doing anything yet. It's not, I mean, we've got the hardware parts of the BMC. We don't have it being a BMC. So of course, we need some open software. I guess going back a few levels, Linux already exists on Microwatt. That's not something we've done. Linux already exists as a BMC in the OpenBMC space. So our bring up focus here is bringing up this DCSCM board with the hardware that we've just produced in Gateware. And for doing that, we have all manner of open source software, which I'm sure you're sort of already familiar with. And here's kind of, I guess, our story of how we're bringing that up. So of course we need a bootloader. For that we used industry standard U-boot. The port, I think it's upstream of U-boot, already supports the Microwatt core. We just needed to add a few, like a platform definition and some bits for reading, boot payloads off eMMC and all that sort of thing. So the Microwatt port's already there, already has the Ethernet controller, already has all our bits there. We just need to define the DCSCM platform for U-boot so we know which hardware's out there, what it can interact with to actually start our bootloader on our new bit of hardware. That work was about 32 patches worth on the sort of the mainline U-boot tree, so not a whole lot, but just our platform definitions, getting that going. Once we have a bootloader, we want to actually boot something, and in our case, that is suspense Linux. Again, Linux already boots on microwatts. We already have the core covered. We just needed to add some of the drivers for our BMC peripherals, the actual the platform definition again. It's kind of similar to the efforts we did in U-boot, kind of replaced with production Linux drivers for this. So we have about 37 patches in total for the Linux port of our DCSCM board. And nothing too controversial there, just, again, some device trees, some bits of driver plumbing and that sort of thing. So we've got our OS layer. We have our server connected to our actual BMC, and now we're booting Linux. And of course, once we've booted Linux on something, we'll benchmark it, right? So back to our 100 megahertz computer. On the numbers in kind of the fourth row are the benchmarks from the existing BMC on that server, which is our ARM core running at 800 megahertz. The arrows indicate whether higher numbers are better or worse. And our relative column on the right gives us where 1 is equivalent. Numbers are higher than 1 are where the microwatt core is doing better. Numbers below 1 is where we're not quite there. So it's sort of percentage of what's in the current production machine. And this is pretty cool. We're running an FPGA core, running at 100 megahertz. We're doing better in some benchmarks, which is kind of cool. We're doing absolutely awfully on our null syscall benchmark. And my theory on this is that we're missing out on some optimization required for the null syscall, but we can ignore that for now. Turns out it wasn't super important. But so we have decent kind of IPC type performance. OpenBMC, which is our BMC payload, we'll get into that later, is very heavy on IPC. So that's kind of the things we're focusing on. So our message passing benchmarks, pretty good. We have some excellent speed in memory access, which is also great. The network performance at about 62% is not fantastic, but it's not super critical. And we're not doing a huge amount of data transfer over the network to our BMC. We have a few artificial benchmarks, just the boot time of our OpenBMC system, which are about parity on, but we did have quite a cut down system at that point. And OpenBMC being pretty heavy on the IPC uses dbus a lot for its internal communication. And we're kind of a bit, this is my concerning line here, our 37% performance on dbus. Everything else is kind of cool. We've got network, we've got flash, we've got system call behavior on our microwatt core running at 1/8 of the clock speed of the thing we're replacing. So that was pretty cool. As part of the project, we kind of we did this about midway through to figure out whether we should keep going or not. And this was quite encouraging. I guess ready to we can't do it, but this table was kind of handy to provide a bit of encouragement. So using a bit of this data, we continued along for some work on OpenBMC. So this is a open implementation of a BMC, but nothing new here. The existing AC922 BMC already supports OpenBMC. The code's all upstream. We don't need to worry too much about that side of things. What we do need to do is provide the platform definition that boots OpenBMC on our new bit of DCSCM hardware. So I think every upstream OpenBMC platform is currently on the ARM architecture. We had to have a power support for that now, given our microwatt core is a power architecture. It's not an ARM device. So we had to do the bits required to make a power-based OpenBMC system. Like I said, platform definition. A couple of patches to the tool chain to allow it to support the microwatt architecture, because we're missing those vector registers. We have to patch the tool chain very slightly to do that. We also trimmed down OpenBMC a little, removing a few of the services, because we're such a small CPU in this case, removing some of the services that we're certainly not going to need, like some of the debug support we can pull out, so that we have something that's actually going to boot and provide some decent performance on a 100 megahertz CPU. That base support of getting just kind of the OpenBMC system itself booting was about 19 patches, and that's kind of getting the thing booting to shell, not talking to the host just yet, but getting an OpenBMC user space all booted at that stage. So reviewing our progress here, we have a server connected to an actual BMC, it's booting Linux, and it's running actual BMC software at this point, which is kind of cool. We're at the point where we can actually access the web page exported by our FPGA BMC. This is the standard OpenBMC UI. It already existed. We're not doing any of this. So this is just the standard OpenBMC software running on the port of our DCSCM FPGA hardware. So this is the default page you get when you visit it. The 100 megahertziness is definitely showing at this point. The web page takes is not quite as snappy as you expect for one of these things, but it's usable, it's tolerable. We're still missing a lot of things. We don't have any inventory data populated on the system. We're not pulling much out from the core, but at least we have our web page here. We can do some basic things on that, including checking out some of the sensors. So this was without doing much on the host bring up side. We already have our BMC definition for the AC922. We just ported it, and we kind of have all our sensors listed, ready to go. So we've got essentially our BMC running, but not talking to much at the moment. So the next phase of bring up is getting it communicating with our OpenPower. So our OpenPower BMC communicating with our OpenPower server itself. Again, important aspect of that is the firmware for an OpenPower machine is all open. We can refer to it. We can refer to the documentation. We can see the bits that are out there when we're doing our BMC bring up. Now, like I said, the platform support is already there. We're just doing the DCSCME parts of that, and that meant that we can, we have access to the code. We can modify it. We can change the platform definitions to suit our new BMC device. So what we're doing here is taking our OpenPower port, our OpenPower board, applying that to our new OpenBMC platform. Now, it's already a thing. So the AC922 BMC, like I said before, is a upstream device. What we're doing here is all of our lots of platform definition bits that get it running on Microwatt, plus the BMC hardware, plus all that, using the existing AC922 BMC definitions. Fortunately, it's kind of not that modular on the hardware. There's a lot of hard-coded things about paths in sysfs for where you find your temperature sensors and that sort of thing, which was not great. There's some awful hacks in our port. We had to fake up a few GPIOs where they didn't exist through that connector, for example. We had to extend a few timeouts. We're running pretty slow, so we had to stretch a few limits there. I guess the talking between the two machines support was about 9 patches to OpenBMC in total. It's not a lot, I guess. And the major factor in that is that we're starting with an open base on the server side and an open base on the OpenBMC side. One of the cool things is now we're dealing with everything open. We've got our open hardware. We can look at, I guess it's like any sort of standard bring up project, with a key difference is that if you find a bug in the hardware folks don't just tell you to get bent. We can actually work on fixing that. And in one case, we found an issue from our original schematic where there was apparently hardware folks don't do off by ones, they do off by twos, where had some of the signals routed a little incorrectly. We can file a bug, and about 2 weeks later, the Ant Micro folks who are in this repo had fixed it in their designs. Now, of course, fixing their designs is great, but we still have our physical piece of hardware which is not fixed. So we had to do some rewiring and do that sort of thing. But again, since we can see the schematic, we can see the board layouts, we can do those sorts of fixes without having too much involvement with the upstream folks if necessary. So once fixing all of these, once kind of doing some little bits of gateway rewrites, we actually had our BMC ready to go. We can go to our page on the BMC web interface and click the power on button. Now, after an extraordinarily long amount of time, we get this. So this is on your left-hand side, we have the console and the server itself. On our right-hand side, we have the console of the BMC. Just a little comparison. On this side, we have our just the top of the CPU information file, our Power 9 CPUs, of which we have 128. On the right-hand side, we have our that's the entire CPU info on our BMC. But the really cool thing is that now we've got the same architecture across both of these, both open power machines, one supercomputer, one tiny computer. So kind of tracking our thing here, we've got our server. It's connected to, through that interposer, the actual BMC. BMC is booting Linux. BMC is running BMC software. And it can boot the server. And even better, it can boot the server running an entirely open source firmware OS. There's nothing in the stack here that's a closed source. I didn't thank me just yet. I did say literally everything is open. There's one component, one little thing, which is the tool chain required to compile a gateware. For that particular FPGA is not yet open. There are other FPGAs that have support in the open source toolchain, and there's also some effort in adding the Xilinx support into the existing place and route tools. So that's kind of, I guess, a bit of prospects of the future. So yes, yay. A couple of not so great things. It's a little slow. We are running on a 100 megahertz computer here. Interestingly, we did kick that technical debt down to this slide, in which we have about 30 to 50% of our CPU usage is in just doing the I2C and the FSI. So just twiddling those GPIOs is costing us a lot of time, which is kind of good news in that it's a fairly linear fix to get some gateware now for the I2C bits and the FSI bits as well to reduce our CPU load by 30 to 50%. So that's kind of cool. So that's our kind of thing there. It was a pretty quick bring up project, so we weren't going through and doing a lot of polished work. At least I wasn't. So there's a bit of kind of edges that we can clean up and sort of a bit of polish we can put on it. But it's certainly, we've showed that it's feasible. We showed that it's some low-hanging fruit that we can work on to fix. And we have our entirely open stack. Again, just reviewing what we got here, we've got our core, IOs, everything open source. Cool. So I just got it. Yes. Yeah, I'll take some questions.
As time's running out, maybe just one question.
I just want to buy one.
Okay.
Sorry, got some bad news for you.
Any plans for incorporating some kind of video input so you can have that on the console, or is that not enough pins on the FPGA?
Certainly, there is enough pins. My concern with that is the amount of gateware, the amount of FPGA usage required to re-encode a video signal. There's a few. The way that's done on the BMC that's already there is that there's a PCI device, which is a video card on the BMC itself, which can either output to a physical video connector or it can re-encode that back into something you can stream over the network. That's going to take a lot of LUT usage to get to that point. And I guess the folks on the video encoding side would certainly have a better idea of how much is used there. Do you know about? Are we?
He was asking about VGA, actually.
Yeah, my worst. I love the UARTs, not so much the video output. But yeah, I think it's a pretty commonly used sort of usage model in getting the video shared over the network from there. But yeah, it certainly don't have it implemented. But again, open source, there's certainly scope to grab some VHDL that implements a video device and kind of wrangling that into the thing. We might be struggling with encoding that over the network at 100 megahertz. But you know, if there's clever hardware engineers around, we could kind of handle all of this in the gateware itself, which could be cool. Awesome. Yes. Just wait for the mic if you. Okay, we'll chat afterwards. Awesome. I'll be around for the entire conference. I'm happy to chat. Happy to geek out about any of the bits here. But here's our resources. A lot of these are on, so the main link here is kind of basically a text description of this talk with a few extra side tales about bring up problems. And the rest of the resources are also linked from that page. And thank you very much.